Hello everyone, welcome to the course. Today's topic will be human AI collaboration. That means today we'll dive deeper into the interaction of the AI tools that we built so far and their human counterparts. So the decision makers that use those tools to make better decisions, for example, in medicine when it comes to detecting tumors on CT scans, when it comes to financial decisions, and so on. So we want to understand, how do humans behave when they interact with AI? In the logic of our course structure, you can see that we covered the AI cycle for a single entity. That was the AI life cycle over here. And now it's about AI in systems, where we talked about the foundation models, the methods that we have at hand when it comes to learning across entity borders, system-wide learning, and now finally human AI collaboration, before next time we will look on creative AI as well as AI ethics and fairness. Now, let us have a look at the objectives. So what are the learning goals of today's lecture? First of all, I want you to explore what the idea of human collaboration is. So what does that cover? What does that entail? What different mechanisms and phenomena are at place here? And especially why it's practically relevant to think about these topics, right? So far, we dealt a lot with technical aspects of AI, but you will see that the behavior of humans interacting with AI might in a lot of cases be even more important than the precise ways in which we designed our AI system, way more important, for example, than the precise performance that we reached in the end. So that those topics I want you to explore. Second, I want you to understand how humans can complement AI characteristics, and also how and when they can or should rely on AI recommendations. I want you, third, to intensify your knowledge on different mechanisms of human AI collaboration. So how does that work in general? And finally, I want you to be able to apply the concepts of uncertainty quantification and AI explainability to your own AI artifacts that you're building. Now, let's have a look at the agenda for today. First, I want to give you a short introduction on the terms and motivate why is it worth talking about human AI collaboration in the first place. Then I want to talk about complementarity, so the idea that both human and AI have something to contribute towards a common goal. I then want to talk second about appropriate reliance, so how do people rely on AI advice, what do we know about that. Third, I want to talk about uncertainty, so AI displaying its uncertainty, and then finally about AI explanation. So let's dive into it. Why is human AI collaboration an interesting topic? And I think in order to answer that, we can go back a big step in time. Let's go back to the first time that humans interacted with machines, 1769. That's a very interesting point in time, because that was when the steam engine was introduced. And the steam engine could automate processes that were typically being performed by humans, by the workforce, right? So you can see an exemplary picture over there. And that led to a very interesting discussion, as you can see already here. It was a lot about the workers versus the steam engine. Who will perform better? Who will be faster? Who will produce the better quality, right? It was this contradiction, this fight of machine versus man that started there. And that's very interesting, because we can see this discussion being continued. Let's fast forward to 1997. A very interesting point in time for AI. That was the time that the former grandmaster, so one of the major chess players, Kasparov, a Russian chess player and the world champion at that time, played not versus another human, but played against a chess AI from IBM called Deep Blue. And Kasparov said, well, no machine will ever be as good as us humans in playing chess. It involves a lot of creativity, forward thinking, no machine will ever be able to perform that. Well, in that case, it was proved wrong because Kasparov lost against Deep Blue, right? So starting from 1997 on, the best chess player and chess players in the world were computers, or in short, AI. So it was, again, this narrative of who is better, humans or AI. And this trend continued. Let's move to 2017, when Google showed very impressive results in playing Lee Sedol in the game Go, which is a very popular Asian board game. People say it's more complex, involves way more strategies than chess. So it was also said there that it is absolutely undoubted that an AI would ever beat the best human players there. But again, it did happen in 2017, and Google also adapted their AI solutions then to other games like chess and so on. So again, we could see AI won those games. And if we move even further now to today, we can see modern solutions like ChatGPT. And again, these questions are coming up. Which jobs will ChatGPT replace? Who is better at performing this task? Is it the AI or is it the human? Will we as humans become obsolete? And there are quotes that support that, scientific quotes, right? Like there's a 50% chance that unaided machines can accomplish every task better and more cheaply than human workers within the next 45 years, or that by 2055, half of today's work activities could be automated with the help of AI. So I think it's very interesting to look at that narrative, humans versus AI, and there could be no better motivation for talking about human AI collaboration. And this development, it sparks the question on, will AI take our jobs? And there's a theoretical concept, a theoretical lens on that question. From Wang and Russ. It's back from 2018, but I think it fits nicely the idea of which jobs could be automated. And what they do is they separate the types of jobs into different stages. The first one being the mechanical jobs being replaced. Those are factory jobs and so on. The second one are mechanical and analytical jobs being replaced, right? You can see now the analysis of data, for example, becomes part of that job profile. Then finally, stage 3, which is about the mechanical, analytical, and intuitive job replacement. And then we have the final stage where it's about replacement of all intelligence levels. Now, and what you can see is that they don't put a specific time point here, but they say 4 different time points. And first of all the mechanical jobs, the share will increase of those jobs being replaced, then the analytical ones, then the other ones, and then finally the empathic jobs. And you can see that the share of humans performing those gets lower and lower over time. So much for theory. But that prompts a question on what if we can choose, what do we want the AI to do? And what do we want to continue doing ourselves? Well, it depends a little bit on the difficulty level of the task. The first level would be automating what humans don't want to do. So everything that we don't like, that we believe is tiring, things like documentation, scribing, protocol compliance, and so on. So everything we as humans basically do not like to do. Second step is scaling anything that we as humans practically cannot do because we are limited in terms of our cognitive capacity, or because we get tired over time. So richer documentations, continuous assessments all the time, long-term monitoring, managing complexity, things like that, right? So first level, automating what we don't want to do. Second one, scaling what we practically cannot do. And then we have the third level, which is performing what we as humans do, but on a superhuman level. If you recall our definitions in the very beginning of this course, we talked about artificial super intelligence. And that is definitely something that's happening in the future. Things like large language models, or before artificial super intelligence, even artificial general intelligence. So intelligence on a human level, right? So those are the different things that an AI could do if we can choose, if we want to think about that. For the remaining lecture, however, I have a certain concept of human AI collaboration in mind. And there are many different more. We cannot touch upon all of them. In fact, we do have a specific human AI collaboration course which deals with all these details. But for the remaining lecture, I have a specific concept of human AI collaboration that I want to look deeper into. And that is the following one, right? So this is our assumption from now on moving forward. And that is that we have an AI system which gives advice to a human. And we call these scenarios human in the loop, meaning that the human involvement is essential here. Maybe because it's required by law, or we want it that way, anyhow. So the human makes a final decision. And in this simplified view, this always means we have an AI system which gives an advice to the human, and then the human makes the final call, the final decision, right? So the human decides, will this person receive a loan or not? Is that a tumor on the CT scan, right? What is the price of this this article that I'm selling or buying, things like that. And that's human AI collaboration in a narrow sense, right? So we have this clear structure over here. And this final decision of the human is what we call reliance behavior. So will the human rely on the AI advice or not? And to simplify it, in many cases, today I will talk about binary decisions. Of course, this is applicable to multi-class decisions. Of course, this is applicable to regression tasks. What I also assume now is that there is a ground truth so that we can check the quality of the AI advice against that ground truth, and also the quality of the human decision, of the reliance behavior in the end against this ground truth. So those are the assumptions for today. And with that logic at hand, I want to look at a few different phenomena. The first one being complementarity in the relationship between the AI system and the human. The second one being the appropriate reliance, or in more general, the reliance behavior of the human in collaboration with the AI. Then I want to look at mechanisms, how an AI can express itself, can explain itself, and firstly, that is the AI's uncertainty in its decision making, which is the third chapter today. And then fourth and finally, how can AI issue explanations to provide reasoning on its inner working? And let us start off with complementarity. What is complementarity? So in a broader sense, complementarity refers to a relationship or quality in which two or more elements somehow enhance or complement each other by performing different yet independent roles, and together they achieve a more desirable outcome compared to a case where each of them would have done the task alone. So complementarity emphasizes both synergy but also independence. And especially in the interaction of humans and AI, that means complementarity is this interplay where human skills and machine capabilities augment each other. And how that works, we'll see on the next slide. Because generally we can aim to collaborate by leveraging complementarity capabilities in different ways. And we can talk about different levels of human AI collaboration there, right? The first one being that kind of narrative that I started with in the beginning. It's either human intelligence or artificial intelligence. It's this versus character, right? This fight for who is better, who is faster at a task, right? You can argue that this is not even a case of human AI collaboration, and I agree with you, but it's like the first starting point here. But that's not the interesting one, as you will see by the end of this lecture. The more interesting case is the next level, the intelligence augmentation. And there are a bunch of research papers that address this. Terms that typically float around here are hybrid intelligence or machines as teammates, and so on. But intelligence augmentation is all about one entity augmenting the intelligence of the other entity. So first of all, there's human intelligence augmentation. That means the AI in this scenario augments the intelligence of the human. So it assists the human in decision making in a task that the human is performing. But it can also be the other way around, that a human helps out the AI. So the artificial intelligence is augmented here by, for example, labeling data for the AI, right? But you can see in the center of both of these cases is one of those intelligent entities, either AI augmenting human intelligence or human augmenting AI intelligence. Now, the final level that we are aiming for, right? You could say the highest stage, the highest level of human AI collaboration is hybrid augmentation, meaning both AI and human working on eye level on a task, right? Like you would in a real world team. And that's typically what we're aiming for. But to understand that, we first have to look at these typical different levels and stages, right? And of course, you can make jokes about all of that and who complements who and who helps who and how. Now, I want to start with two interesting real world cases that should make clear why human AI collaboration is so important. And I really like this first example here from Zillow. So Zillow is a US-based company, and what's interesting about them is that they have a huge market in the US. And I want to look at a particular situation which is already a few years back. So what Zillow did introduce was an AI-powered tool for their home buying business. This is, by the way, often referred to as iBuying. So there was an algorithm that was designed to predict home prices and then enable the company to make quick offers on homes. So instead of a human looking at every home, you would have this AI tool assisting you in that. Now, fast forward to the year 2021, especially the late half of 2021, this tool contributed to Zillow's loss of $500 million because the AI's prediction did not account for the inside information advantage that homeowners had, especially such as the knowledge of idiosyncratic characteristics of their home that might not appeal to buyers, but which are variables outside of Zillow's model, right? This model didn't cover that. And especially when the real estate market began to cool down in 2021 due to the COVID crisis, the shortcomings of this AI tool became more apparent, right? So while the algorithm could predict home prices with a certain level of accuracy, the rapidly changing market, however, the market conditions due to the pandemic situation were too complex for the algorithm to handle effectively. I really like this example because it's both a case for human AI collaboration, because this led to Zillow making pricing errors, both when buying and selling houses, because they automated this process. Because humans as you recall the earlier graphic, because the human in the loop was not utilized in a way that it was meaningful, right? Good case for human AI collaboration. That's the first point why I like it. The second one is, it's a great case for concept drift detection that we already discussed as part of this lecture, right? Because we had external changes and they were not accounted for by the model, right? So this case of Zillow has been a significant point of reflection on over-reliance on AI, because there were not the right tools in place that will make sure that humans control what the algorithm was doing. And this example typically serves as a reminder of the limitations of AI and the importance of human judgment in these business practices. That's one way of looking at it, the Zillow's example, why we need human AI collaboration, and in fact why we need effective human AI collaboration that works. But with humans, collaboration is not always so easy, right? Let's look at this case from Forbes over here. So where a lawyer used ChatGPT in court and cited fake cases, right? So what happened here is that the lawyer for a man suing an airline in a routine personal injury used ChatGPT to prepare a filing by the way, something that happens more and more as we see in statistics. But the AI that it used delivered fake cases, right? It hallucinated these cases. And I hope by our fundamentals in foundation models, you know why this is happening, right? And the attorney presented this case to court, prompting a judge to weigh sanctions as the legal community grapples with one of the first cases of AI hallucinations, making it to court. There's also another case of a Canadian lawyer. She also used AI for legal research, and also here, fake cases were created, and this was taken to the courtroom. So what you can see here is obviously there seems to be a tendency for humans not necessarily relying on AI, but relying on AI in the wrong case. In both the Zillow example, where potentially not even a human was involved, or in these case of the court rulings over here that you can see. Of course, the capabilities, and that's something that I should note here, the capabilities of AI do change over time, right? So this hallucination issue is one that all the major technology brands are working on. Let's see how this is fixable in the long run. But we have to think about human AI collaboration also with this time-sensitive perspective, meaning that the capabilities will shift dynamically over time. And both of these cases, or these three cases, I think are a really good motivation to look at complementary team performance. And to illustrate what we're talking about, let's take error metric into consideration. And this is an error metric like the mean absolute error, for example. It doesn't really matter what type of error metric it is, but the lower, the better. And with that, I want to demonstrate what complementary team performance is and why complementarity is important. Now, let's say we have a task at hand. And by the way, that is something that we've done empirically also with a bunch of different cases. I'll give you access to the papers. And now we give that task to an AI, and we can see the AI performs pretty okay at that task. We can definitely see the AI performs better as the human, right? That's an example over here, but we saw that behavior across many tasks and many different fields. So that's not entirely made up. Now, you could stop at this point, right? This is the discussion that we started with. Oh, it's always humans against AI. Who's better? Okay, the AI is better, so the AI will take over all our jobs. Now, what's interesting is that this view doesn't look at the combination of human and AI, so actual human AI collaboration. And different cases can arise, right? We can have human and AI working together, reaching this error over here. Again, the lower the better. So better than the human by him or herself. Or we can reach performances around here. So even better than the AI. And of course, that is a fundamental difference. If we are over here, that would mean we would automate the task at hand. If we're here, we would say this is definitely a good case for human AI collaboration. And the definition of that case down here is complementary team performance. And complementary team performance is exactly that delta over here. So it's about the difference in comparison to the best performing entity, which in many cases is the AI, which in some cases is the human. But what we do see here is that there can be the case where the combination of human and AI is better than any of these isolated entities. And that is complementary team performance, CTP. And obviously, we should design for these cases because it's a good case for humans in the loop and because it's a good case for the task at hand, because it means we perform this task to its best possible solution. The question now prompts is, how do we get there? How can we reach complementary team performance? And to understand that, we have to look at the complementary potential. To be precise about the distribution of the individual strengths of both human and AI. And you can have this complementarity across tasks. You can have it across instances, or you can have it within an instance. And the example that I'm going to do right now is based on instances for a task. So each of these points is an instance over here that can be predicted by either a human or an AI. But this logic also holds true if you imagine that these are single tasks, or this is an instance which can then be classified by two different entities, a human and an AI. So for the time being, let's say these are a bunch of instances, right? These are houses where I want to predict the price. These are credit loan applicants where I have to make a decision whether they will receive the loan or not. Take what you want, yeah? And now let's say for those instances, the AI is able to make a prediction, right? So the AI has its strength on those 9 instances. Now let's also imagine we take the human into consideration, and the human is able to predict the exact same instances, right? So human and AI are accurate on the very same instances, on these 9 instances that you can see over here. What is the result of that for complementary team performance, and especially for the complementarity potential? Well, in that case, we have no complementary potential, right? They're both good on the same instances. And because there's no complementary potential, there's also no way of enabling complementary team performance, right? They will perform the same. Now, of course, that's a made-up example. In reality, it will look more like this one over here. So that means there are a few instances where human and AI are accurate on those 3 over here. So they're both good on predicting these. But then there are a few instances that the human is able to predict, as well as a few instances that the AI is able to predict. So human and AI are accurate on different instances. And that means now we have complementary potential. Now complementary team performance is possible, because now we can start combining the strength of the human lying on these 6 instances over here, and the strength of the AI on these 6 instances over here. And this now enables us to work together and reach a solution that is better than those 2 individual entities on their own. And now let's look at the maximum theoretical case, which is something like that. So human and AI are accurate on entirely different instances. And this obviously leads to a maximum in complementary potential. And that still means in those cases, complementary team performance is possible. So in an ideal scenario, we know exactly when to delegate a task or an instance to a human and which of these should we delegate to the AI, right? In that case, we would say, okay, the human's going to predict those instances and the AI is going to predict those instances. And then we could reach, we could utilize this complementary potential to reach complementary team performance. However, in reality, this threshold is very tricky to navigate, and it's subject to a lot of factors. For example, from a cost perspective, companies are incentivized to automate most of the tasks. On the other hand, humans often struggle with estimating their own capabilities. And what we also know is that, recall our logic of human AI collaboration from the beginning. In reality, in many cases, we have to have this human decision maker. So even if the AI does the prediction for these cases, the human still has to approve it. The human still has to appropriately rely on the AI. So a very important concept that we need to look at right now is, let's assume we have complementary potential and we aim for complementary team performance. How can we make that happen? How can we make sure that the human also appropriately relies on those predictions that the AI did? And that's why we'll talk now about appropriate reliance. We can position appropriate reliance in this interplay of AI system, human decision maker. At the stage where the human receives a recommendation from the AI and then makes his or her final decision, potentially by relying on the AI or relying on his or her own skills. And the interesting aspect is that a lot of things can happen here when we present humans with AI recommendations. And the one phenomena that we can observe is over-reliance, or in other cases also often called automation bias. So according to Montier and Skidka, automation bias is the tendency for individuals to over-rely on automated systems, like AI, to the exclusion of other informations or their own decision-making skills, right? You could see this over-reliance behavior in the two examples that I showed you earlier, right? On the attorney utilizing ChatGPT because he or she would simply trust whatever the system output, even though those were fake cases. Or the other case of Zillow, where people would trust the algorithm so much that they would give it the opportunity to automatically buy and sell houses. So apparently, we as humans often have a tendency to trust the decisions of an AI system without fully considering other options, and potentially also without using our own judgment, our own cognitive skills. And obviously, as you could see from the introductory examples, this can lead to problems, and especially to a lack of critical thinking on the part of the human. Now, I'm not judging that behavior, it's just something that we empirically can observe. And there are a bunch of reasons for that. First of all, it's the perceived reliability and accuracy of the AI system, right? Maybe I observed many cases where the system did well. It's the assumption that the AI system is objective and unbiased. It might also be a lack of transparency and understanding of the AI. So how does it make their decisions? And then finally, let's be honest, it's laziness. It's the ease and convenience of relying on the AI system rather than using your own thinking, because let's be honest, that needs energy and we all want to consume as little energy as possible, right? So that is one phenomena that we can observe across a lot of different studies, that if we equip humans with AI systems, that either at the beginning or over time, they will over-rely on these systems. And that's what we call automation bias. That's the one extreme that we can observe when humans interact with AI. However, there's another one, and that is under-reliance, or also called algorithmic or algorithm aversion, right? And according to Yusupov, algorithm aversion is a biased assessment of an algorithm, which manifests in negative behaviors and attitudes towards the algorithm compared to human agents. So humans often have a tendency to assess the algorithmic output, so the AI recommendation, less favorably than a human output, and potentially even ignored entirely, even in cases where it would be identical. And this can lead to fundamental problems, right? Just as it is the case with over-reliance on AI, this means we now over-rely on potentially flawed human decisions, just because they are human. So you can see there are these two extremes. Now, what are the reasons for algorithmic aversion? First of all, again, the perceived performance and capabilities of the AI system. Maybe the AI did an error early on when I interacted with it, and that's when I stopped trusting it. It might be the lack of human agency and involvement. It might be the preferences, right? I rather talk to a real physician, to a real lawyer, right? To a real world decision maker. I have a preference for socially closer human agents, right? Like my friends. Or I have a general distrust in technology. And there are a bunch of reasons for algorithmic aversion. Now that we covered the two extremes, over-reliance and under-reliance, or automation bias and algorithmic aversion, let's have a look at what we're trying to actually aim for. And that is the concept of appropriate reliance. And I want to make this really, really clear in an illustrative example over here. Again, think of a decision system where we have a human receiving an AI recommendation and then the human making the final call. Now, to understand appropriate reliance, we first have to ignore the AI advice. So let's have a look at what would the human do on his or her own. So the initial human decision without any advice of the AI, right? This human has never seen any advice. What would that person decide? And for the sake of simplicity, let's say it's again a binary decision case, so something's either correct or incorrect. And we can distinguish between two cases here. The initial human decision is correct or it is incorrect, right? Now, let's say this human receives an AI advice. Now, the AI advice itself can, of course, be also correct or incorrect. And now, to understand appropriate reliance and to conceptualize it, we have to look at the final decision that the human makes after receiving an AI advice. Let me make clear, it's not always the case that the human makes up his or her mind up front in the first place, so this step over here. But to theoretically grasp the concept, we have to look at what would the human have done on his or her own, because only then we can understand whether the decision changed on the human side. So from this combination of initial human decision and AI advice and whether it's correct, different cases come out. The first one is under-reliance. So my initial decision was incorrect, the AI advice was correct, but I rely on my own initial decision. That is the case of under-reliance, in more general terms, algorithmic aversion. Let's look at the other extreme, that is, my initial decision was correct, but the AI advice is incorrect. I do rely on the AI advice, however. That is over-reliance on AI, in a broader sense, automation bias. And now, the two scenarios that we want to aim for with appropriate reliance is correct self-reliance in the cases where I myself am correct and the AI is incorrect, and correct AI reliance for those cases where I myself as a human am incorrect, but the AI is in fact correct. And that is the conceptualization of appropriate reliance. It's those two cases over here, and especially aiming in the design of AI, in the design of human AI collaboration, aiming for these two cases of correct self-reliance and correct AI reliance. And this appropriate reliance means it's the sweet spot between the two extremes that we talked about earlier. Algorithmic aversion on the one hand, the complete avoidance of AI support. Automation bias on the other hand, blind faith in any AI support. What we aim for is this sweet spot in the middle. That's appropriate reliance. And let's be honest, there are a bunch of open questions on how we can reach that, but that's definitely a challenge that we need to tackle, because if people move into these extremes in their behavior when they get the chance to interact with an AI, we will have a problem sooner or later. And I think the problem's rather soon, because let's look at the consequences on what happens if people over or under rely. It's the idea of human oversight again, this idea of human in the loop. The human makes the final call. But we will question, is human oversight enough? Apparently it's not, because the empiric experiments in our field show that humans tend to go into these two extremes of over-reliance and under-reliance. They still have the final call, but they over or under-rely on the AI. And that means, and that's a tough headline to read, human oversight is often not good enough. And it's especially not good enough for AI war machines, because as you can read from this news articles over here from the Asia Times, humans obviously put excessive trust in these machine systems and their conclusions in warfare, and that has a risk. Like, this has a real world risk for civilians especially. So while we can agree that many high-stake domains can or should not be automated, in recruiting, in legal judgment, in warfare, you can see on the left, and human oversight is legally or technically required, it's still important to know that human oversight on its own is not enough, because people tend to go into these extremes with their behaviors, which means we need to design for appropriate reliance, right? Otherwise, human oversight will change nothing. And to have effective human oversight, we need a bunch of conditions that hopefully make sure that humans appropriately rely. Those ones, however, we will capture more in more detail when it comes to AI ethic and AI fairness, right? So again, I'm not making a case against human oversight, but I do make a case for designing the human AI interaction in a way that it is beneficial, that the humans appropriately rely on AI advice. And again, what does appropriate reliance mean? It means relying on yourself when you are correct yourself and relying on the AI when it is correct. I know that's a theoretical concept. It's easy said. It's way more easily said than done, but still it's important to note that. Now, me and my colleagues have looked at a lot of different appropriate reliance studies out there in different fields, right? We mapped them and we looked at were those objective decisions that were being made, were those subjective ones. Now, for today's lecture, we will only look at the objective ones. If you recall, there's always a ground truth. We always know what is correct. But as you can see from that paper, and I can't again go into detail, but I'll link the paper below. We see a lot of different application areas in a lot of different fields over here. In some cases with objective outcomes, in some cases with subjective ones. But as you can see from all the studies that we looked at, this obviously applies not to a single domain, but to a bunch of domains. And we're still figuring out how we can enable appropriate reliance, and we still need a lot of work to understand if and how people appropriately rely. But for the time being, it's important to appreciate that we understand the importance of appropriate reliance. And now the next step is to understand how do we design systems and how can we get into building systems that enable, or building interactions that enable that appropriate reliance. One solution that is frequently mentioned here, so as a design principle to reach appropriate reliance, is uncertainty quantification, or more precisely, displaying the uncertainty of the AI. So in the logic of our conceptualization, this means, again, we have this human in the loop scenario. Over here, now our AI system somehow communicates its certainty or uncertainty towards the human. That means when I, as a system, make a prediction, I will also clearly communicate to my human counterpart how sure am I about that decision, right? There are different ways on how this can be communicated. This could be textual, that could be a percentage in uncertainty, but it will definitely or hopefully help the human. I'm not saying that displaying uncertainties per se helps to enable appropriate reliance, but it's often debated that if the AI would simply reveal its probability scores, its uncertainty, then it could assist the human in better relying on the AI decisions. And I think that that makes sense. But if we want to utilize uncertainty, let's have a quick look at the metrics that we have at hand. More precisely, the uncertainty quantification ideas that might steer appropriate reliance. And there are two fundamental uncertainty types that we have to distinguish. The first one is called epistemic uncertainty over here. Now, epistemic uncertainty is about the model uncertainty. And this is uncertainty that stems from limited data and knowledge. That also means, on the other hand, if you recall our principles of data-centric AI, that this could be potentially eliminated or at least reduced to a certain degree by giving the model access to more knowledge, i.e. more data, right? And that is the epistemic uncertainty. So anything that is based on not enough data to understand a real-world phenomena. The other case of uncertainty is aleatoric uncertainty. So that is data uncertainty. That is due to the inherent noise or the national randomness in the data. This cannot or can never be reduced, right? Simply by adding more data, my epistemic uncertainty will go up, but my aleatoric uncertainty might not change at all. It might even be higher, right? So this means two different types of errors can happen here as well when displaying uncertainty. Errors due to the limited knowledge, the limited data, and errors that happen anyhow due to the natural randomness of the data that we have. And I think it's important to distinguish between those two. Now, how do we measure this uncertainty in a AI-based scenario, especially based on supervised machine learning? Now, there's an interesting concept that was created by Gall and his co-authors, how we can capture uncertainty. And this works with deep neural nets. They use dropouts as an approximate inference of the weight of the different neurons. And by utilizing this dropout, we get an understanding on the robustness of our recommendation. So what we do is, if we have a neural net and we get a classification for a picture, for in this case again binary, is it a cat or a dog, what happens with dropout is that we remove certain parts of the neural net over here and then see how our prediction changes. And this gives us a feeling for the robustness. And if you repeat that, you get a very good measure on the uncertainty of the prediction that can help you with that. Interestingly, dropout was historically more developed for understanding the robustness in the training process, but right now it's utilized mainly right here to capture the uncertainty in the predictions of these models. And that's a great measure, and that's something that we can utilize in the exercise together, and then we can also build tools where we display that uncertainty towards the human. Now, uncertainty seems to be a good candidate of revealing more of the underlying logic of the AI system, but it's only one way to do that. The more interesting and the more broader term here are obviously explanations, or also often called explainable AI, short XAI. If we look into our conceptualization again, this means, again, the AI system will display something. In that case, it's displaying explanations, so insights into its own reasoning on how it came up with its decision. Now, why do we want explainability in the first place? A very famous example over here to display why it's interesting is the husky wolf example. So let's imagine we have a bunch of pictures from huskies or wolves, and we want to predict whether this is a husky or a wolf. And you can see that our model is doing a pretty good job. It only makes one mistake over here where it predicts as a wolf when it in fact is a husky. The other way around would be way more dangerous, as we can see from this news article of the man who accidentally adopted a wolf pup. Spoiler, it did not go well. So probably our model should perform with the highest possible accuracy. Otherwise, people will start adopting wolves, which we obviously don't want. Now, the model seems to be doing a very good job over here, right? It has, in fact, 95% of accuracy. So should we trust the model? Well, that is where explainable AI can come into place. If we look at the simple prediction of this picture over here, we will see that it says it's a wolf, and we can even display certainty scores, like we learned from before, of 98%. So talking about appropriate reliance, you might go with the recommendation over here as a human in the loop. But if we now use explanations, one of the possible explanation algorithms that are out there for computer vision tasks, we see the areas of the picture that the algorithm takes into consideration for making its prediction. And it's not looking at the face area of the animal at all. It's only looking at the background, apparently. And if we do that for all the pictures, it is revealed that, in fact, the tool never looks at the animal itself, but always looks at the background, right? So these are the distinct properties that influence the prediction of the system over here. And what we can see over here is that, well, we did not build a very good wolf and husky detector, but we built a great snow detector. So obviously explanations can help us with that, even in cases where the pure prediction and the uncertainty score cannot help. And I want to give you another example from our own research where we utilized explanations. And one of those cases was with one of our industry partners from the manufacturing industry. What they're producing are these cutting tools over here. And again, I'll make the paper available for you. And what they do with these tools is they analyze their wear over time. They do that to improve their machining processes for customers, and of course, especially for developing new generations of these cutting tools in the R&D department. And what they wanted to do is they wanted to automatically characterize the wear on these machining tools, and based on that, they could provide novel database services to their customers. So if you take an exemplary tool that looks like that, what we would do now as part of this project is we would take microscopic images of each of these tools after they had been used at the customer side. So we would use a microscope. And again, in data-centric AI manners, this means we created our own data set. And then we would have this microscopic pictures of the cutting tools. And no industrial expert here, but there are apparently different types of wear, like flank wear, chipping, build-up edge, and so on. And what we needed then is, of course, an annotation of these images. So what we did is we gave these images to experts, and they would start pixel-wise, as a pixel-wise so-called segmentation of the different wear types over here. That you can see chipping, flank wear, build-up edge, and so on. So we would receive a lot of these images as our ground truth. And what we did next is we then wanted to apply this model to, of course, unseen data. And we could see that in some cases, like here, it would do predictions that look like that, and in other cases, it would look like that. Now, we combined the uncertainty scores with explanations to get a better understanding on which of these cases can be directly utilized and where do we need an additional manual laboring of humans. Again, humans are very expensive, so we do not want to utilize them all day labeling those images. So by quantifying the uncertainty and displaying this via XAI methods, we could, for example, see, okay, the uncertainty over here is only at the edges, whereas here we have a lot of uncertainty, and then there is manual labeling necessary in order to improve the output over here. Now, those are interesting cases for why we need explainable AI. But let's have a look at the fundamental dimensions of explainable AI first. And we can divide explanations into two fundamental questions. The first one depends on the underlying machine learning model. And there are so-called anti-hoc explanations, so-called glass box or white box models. So this is every machine learning model that is naturally interpretable. If you recall our lecture on the different model types out there, these are things like regressions or decision trees. They have an inherent explainability to them, right? We can look at the way that a linear regression separates points. We can look at the way that it tries to cover the relationship and pattern in the data. For the decision tree, we can look at the decisions that are being made that go into the different nodes and leaves in the end. So nothing additional is needed here for these anti-hoc explanations. The models are intrinsically, naturally interpretable. However, you also know by now that the majority of models nowadays are deep neural networks, and those are so-called black box models. And those are not interpretable, and we need an additional interpretability method on top, for example, LIME or SHAP. So there's no way of making this black box model in any way transparent, so we need an additional metric, an additional tool, an additional algorithm to explain the reasoning of this first one, right? So we have an additional layer on top. And the majority of explanations right now are these post-hoc explanations that we are looking at. So these are the interesting ones. However, this also introduces a bunch of challenges, as you will see soon. Okay, so first question is, what is the underlying machine learning model? Is it a glass box model? Then it's directly interpretable by its own. Or is it a black box model? Then we need those post-hoc explanations. The other question that we ask is the globality of it. So first of all, is it a local explanation? So we look at a single instance and ask, why does X lead to Y in this case? So why was a single image classified the way it was? Why did we reject this single loan of this single applicant, right? These are local explanations for one instance. Why did X lead to Y over here? Opposed to that are global explanations. So how does the entire model work in general, on average? What are its decision rules? And we have to look into these different cases and understand, do we try to explain something locally or globally? And also we have to look at what type of explanation is needed in the first place. One very popular type of explanation, maybe the most popular, is SHAP, which is commonly used in a bunch of tasks in both research and industry. So SHAP is a post hoc explanation, so built for black box models. It can be utilized both as a local one, or if we aggregate all the local ones, it can also be a global one. But in the depiction that I'm going to show you right now, it's a local one. So what is SHAP? So SHAP stands for Shapley Additive Explanation. So that's a method, again, to explain the machine learning predictions. And it does so by showing how much each feature contributes to a specific prediction. At least that is what it tries to do. Its fundamentals are not in machine learning, but in fact in cooperative game theory. So it treats the different features that come in as players and distributing the credit for the predictions fairly among them. These SHAP values, they can see in the example over here, are consistent and additive, meaning that they provide clear and balanced insight into these feature importance, as you can see from the depiction over here. So in theory, this makes SHAP a potential tool for understanding complex models, again, like neural networks, hopefully in a human-friendly way, because we can see already which features are utilized and how do they contribute over here to the output, opposed to the black box model on the left side without any explanation. Now, there are many, many more explanations. Let's see how many of those we can try out in the exercise ourselves. But one question that I want to bring up right now is, are explanations helpful? Do they enable better human AI collaboration? In fact, do they help potentially with appropriate reliance? And literature is mixed on that. So on the one hand, there are cases where explainable AI could really help and helped people to identify mistakes and overrule AI predictions where they were incorrect. On the other hand, there are papers that show explanations increase the chance that humans will accept the AI's recommendations regardless of its correctness, right? So without going into detail, because there are a bunch of works going on at the same time, and a lot of them are contradictory, in a nutshell, current research does not agree on the helpfulness and effectiveness of explanations. But context definitely matters. What we do know, however, is that the majority of implemented explanations are post hoc explanations. And one thing that's important to note here is that there can be errors, a bunch of different errors. So while this AI system over here makes now its recommendation, the explanation is, in simplified terms, an additional AI model on top of the prediction one. And of course, we do not know, are these explanations truthful to the actual model? So a bunch of errors can happen with flawed explanations. The explanations themselves can be erroneous. Even if they're not, they can be interpreted in the wrong way, and they can lead to undesired behavior. Let's look at the erroneous explanations first. So the first question is, can we trust the explanations? Do they really explain the reasoning of our model, or do they find some kind of shortcut? So are they trustworthy? Are they reliable? Or are they plain out wrong? And there are many, many cases where explanations do not adequately explain the underlying prediction model. So that's definitely an error that can occur. Even if that's not the case, you can intentionally manipulate explanations, still ensuring their statistical validity, but changing small bits, which is called fair washing. So before, for example, gender played a role, and after the fair washing, by the way, again, still a statistically valid explanation, gender did not play a role anymore. That's what we call fair washing, and there are papers showing how you can do that. So obviously, there can be errors in the explanations themselves. But even if that's not the case, I mean, I just showed you an example of SHAP. The information can be overwhelming. I mean, look at those plots over here. that seems pretty arbitrary. I mean, what conclusions will you take out from these plots over there? So the information can be overwhelming. And this can lead to a bunch of problems downstream, right? I could just simply use that and say, okay, look at this complex graph. Obviously, the prediction of my AI is true. What can also happen is a bunch of issues down the line when it comes to looking at sensitive features. So where does discrimination really start? I mean, even fair washing aside, am I aware of all the important sensitive attributes over here? Were some left out? Am I aware of them? Am I not aware of them? So how can we ensure fairness in these structures? Again, something that we'll discuss in the very last lecture, but I want to at least hint at it at this stage. And then finally, this can lead to problematic behavior. First of all, you can use explanations simply as a placebo. So here's a complicated decision outcome. And by the way, here are a bunch of explanations. Go ahead, use that. But does it really help people to understand the reasoning? Do they just decide what they wanted to decide anyhow and use explanations as a placebo over here? There are a few studies that show that. On the other hand, what about the alignment with existing stereotypes and biases? Maybe explanations help here, or I only look at the explanations that by chance fit well to my existing stereotypes that I have in mind. So as you can see, while the idea of explanations is great, down the line, a lot of things can happen. And I want to shed light on one more work that we recently did on the first case over here, on these erroneous explanations. Because if we think about the fact that explanations can be wrong and that they don't have to align with the underlying prediction model, this again adds a new layer to our conceptualization of appropriate reliance. Because right now, we do not only have the cases where we have an initial decision of the human and the AI, but the explainable AI, the XAI advice, can now also be correct or incorrect. And that means from that, even more cases stem, right? Because that means now we have two cases of under-reliance over here. Namely those ones where my initial human decision is incorrect, the AI advice is correct, but then my explanation can be correct or incorrect. Based on that, we can distinguish between different types of under-reliance that can stem from different causes here. Same goes for over-reliance, right? So that means it gets more complicated because we have these two layers, the prediction layer, the AI advice by itself, and the explanation layer. And because these are post hoc explanations in many, many cases, errors can happen. Now, we wanted to understand better what this means and how do people deal with incorrect explanations. So we did an experiment, and what's interesting is we did this experiment with experts and non-experts. So we also wanted to see what happens to these two different groups. Are experts able to spot these errors in explanations or not? And again, I'll link the paper, but in a nutshell, I want to quickly show you the results. So we looked at, can we reach complementary team performance? So in the end, do people appropriately rely on the AI advice? We tried two different types of explanations, natural language based one and example based one. And we set the AI performance to 50% willingly. So it did make errors in the case. And what's interesting is, so if you look at the human performance where we gave this task to experts, they were a little bit below the AI performance. But when we combined them, so the combined human AI performance over here, that's the dark gray bar, they were able to reach complementary team performance. So they were able to appropriately rely on the AI, even though the AI made errors and even though half of the explanations were wrong, right? The experts obviously spotted these wrong explanations and it helped them to still identify the cases and appropriately rely. However, we also did that for non-experts for the task. And there it's different. Well, you can see that the human performance of the non-experts is obviously way lower compared to the experts earlier. But what we see is while AI helps them to make better decisions, even though AI makes errors and some explanations are wrong, we see they do not reach complementary team performance. So obviously, you can use explanations here to misguide the non-experts, right? They obviously take these wrong explanations at face value. And what does it mean in a nutshell? It means that if an AI makes errors, and if an AI makes errors in the prediction, also in its explanation, it's not that big of a deal for experts because they can spot those. But what about non-experts? And I think that's a very interesting case. I mean, think about people using chat tools like ChatGPT. They mostly use them for cases where they are not experts. They ask them medical questions, they ask them legal questions. But as they are no experts, they cannot spot whether these tools are correct or incorrect, and they cannot also even use these explanations that are provided. And again, these explanations can be wrong. So you see, a promising field of research lies ahead, and there's much more to be done here. Okay, now let me shortly summarize what we did for today. First of all, it's human AI collaboration is a great mechanism to combine the strength of both humans and AI. But we have to think a lot about the design over here, right? There are different mechanisms in place and different ways on how you can even architecturally build up human AI collaboration. And to be honest, we only covered a very tiny proportion of that today by looking at this easy scenario of AI advice being received by the human then makes the final decision, right? There are way more ways of human AI collaboration out there, where AI teaches the human something, for example, where we have different processes in the way that the advice of humans and AI is combined, and so on. But what all of these have in common is that this idea of complementary potential, complementary team performance, and appropriate reliance should play a really vital role in designing that interaction. Second, we learned that there are two important ideas that can help in fostering appropriate reliance and that could assist more effective human AI collaboration. Those are explainable AI and uncertainty quantification, right? Although we did just see that there are a bunch of issues still with explanations that need to be solved, but in general, there can be cases where it's helpful. And then finally, a lot of soft factors come into place, right? My tendencies, right? My tendency, for example, to over-rely or under-rely, my perceived usefulness of this tool, my trust, my understanding of the tool. And obviously, this also directly influences the adoption of AI systems, and then in the end influences the human AI collaboration, right? So this was just a short, very detailed view on human AI collaboration. There are so many things out there that still need to be discussed, and there's so many different scenarios. But as you can see, it's a very exciting field to do research in right now because there's so much to understand. And tools like ChatGPT did a great job in democratizing AI, but we're still kind of lagging behind a little bit in understanding the mechanisms, the psychology of people interacting with AI. And that's why it's one of the greatest fields to be in right now. Okay, so thank you so much for your attention today, and see you next time. Bye-bye.